So with notes on electromagnetic waves done, we just finished that one, 18. Whoop. We started we started homework 3.2, but didn't quite finish it. So what we did so far on that one was the beginning, where we used the equation that the speed of light equals wavelength times frequency. But now we're going to get into some energy calculations. So that's why we needed the energy notes. Conceptually, it's pretty easy. Compare the following waves. We have this one and this one. Which wave has the higher frequency? Just for, okay, we'll call this one the top wave, and we'll call this the bottom wave. So which wave has the higher frequency? The top wave is occurring more frequently. If one wave represents visible light and the other represents infrared, which wave is which? So sneaking to the top, visible light versus infrared radiation, that's what we're comparing. But I'm actually going to skip that question for now and go on to the next one, where it says which one has the higher energy? Energy, like we put in the notes, energy has a direct relationship with frequency. So the more frequent the wave is happening, the more energy it has. So this one on top is a wave that carries more energy than the one on the bottom, simply because it has a higher frequency. So the second question, where I'm trying to figure out I'm trying to figure out infrared versus visible light. Back up here on the top, I want you to take your orange or your yellow or whatever color you're using for energy, and over here, write low energy, and on this side, we have high energy. By this scale, visible light has more energy than infrared, which makes sense because ultraviolet over here, ultraviolet has more energy than visible. This is what gives you a sunburn. So ultraviolet has more energy than visible. Visible has more energy than infrared. Infrared has more energy than micro, and so on and so forth. So back to the problem. If one of these waves represents visible and the other is infrared, well, visible light has more energy than infrared. That's how it would have to be. Go to the following link, and here it talks about the difference between non-ionizing radiation and ionizing radiation. The word ionizing, so define ionizing, this is when the wave has enough energy to remove electrons from whatever it's hitting. So if it's ionizing, it's removing electrons. Non-ionizing would be not enough energy to do that. On problem 1, label the non-ionizing forms. We're going to call this safe. because it's not damaging your cells. It's not stripping electrons off of you. And ionizing, this is going to be what we consider dangerous because it's so high energy that it's actually removing electrons from our body. So on problem 1, the very top problem, we're trying to figure out which ones are safe and which ones aren't. The ones that are safe, so safe is non-ionizing, 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 and then ultraviolet is where we start getting into things that could potentially be dangerous. This is why we don't want to get a sunburn. That can cause cancer. It's too high of energy and it's dangerous. X-rays also ionize. Gamma ionizes. So the very last question on the paper says, explain why when you go to the dentist, they recommend getting as minimal X-rays right here, as minimal X-rays as possible, and they put that lead apron vest over you to cover your body if you do have an X-ray done. So this is basically trying to minimize your exposure to the ionizing or dangerous light. So this is the conceptual idea. Now hopefully when we move on to the calculations, it'll still make sense. So pause this video if you need to. What we're going to do now is you'll need a calculator because we're going to be doing calculations instead of conceptual stuff with energy. So this is kind of from the notes, the relationship between, between wavelength and energy, or also frequency and energy. These are the two equations, 1, 2, that we wrote in the notes. I like the notes better because it's color-coded. But these are the equations we're going to be using, so have them off to the side with your notes. And we're going to determine the energy associated with a wavelength of 418 nanometers. I'm going to use this calculation, this equation here, because it has nanometers. But I can't have it be in nanometers. I need to first convert it to meters. So off to the side on this yellow paper, if I was going to convert, I have 418 nanometers. I know that there's 10 to the 9th nanometers in a meter. (418) times 1 divided by 1 times 10 to the 9th power equals 4.18 times 10 to the negative 7 meters. This is my wavelength in meters. This is my wavelength in nanometers. Same, just different units. So right above here, I'm actually just going to write 418 nanometers equals 4.18 times 10 to the negative 7 meters. I'll move this paper out of the way. And I'm going to copy paste this formula here. Copy, paste. energy equals H times C divided by wavelength. I'm trying to find the energy. Every time I see an H, I plug in 6.626 times 10 to the negative 34. Every time I see C, I plug in the speed of light. So what this is going to turn into is, let me rewrite this, energy equals the letter H is always this, H, times the speed of light is always this, divided by the wavelength, which I calculated up here, 4.18 times 10 to the negative 7. I took out all the units just so that you could see it a little bit more easily without any of the units, just the numbers. This, in the box, pink box, this is this. I just plugged in H, H, C, C, wavelength from the problem. To get my final answer, I just have to put this in the calculator and see what it equals. 6.626 times 10 to the negative 34. I put everything in parentheses to make it work better. Times 2.998 times 10 to the 8 divided by 4.18 times 10 to the negative 7. Enter. And it's telling me my answer is, it says the energy of that wave is going to be 4.75, I'm just going to cut it off there, times 10 to the negative 19 joules. That's the energy that I'm calculating from that wavelength. When you do problem 9, it's the same exact problem. You're still calculating the energy associated with a wavelength, but instead of having a wavelength of 418 that we converted and plugged in, you're going to have a wavelength of 780 that you convert and plug in. Number 8 uses the other equation because it says the blue color from the sky results from the scattering of sunlight by air molecules. Blue light has a frequency of blah, blah, blah. Now here's the frequency equation. Copy, paste, because we're trying to calculate the energy. Energy equals H times frequency. We're trying to take this equation in the box, and I'm going to rewrite it, but substituting in what H is. H is always 6.626 times 10 to the negative 34. The frequency is right here. It told me in the problem. 7.5 times 10 to the 14th power. not worrying about the units right now. I'm just trying to show that this box is same with this box. I plugged in the stuff. (6.626 times 10 to the negative 34 times 7.5 times 10 to the 14th power equals 4.97. I'm going to round that over. Energy equals 4.97 times 10 to the negative 19 joules. So this one has a little bit more energy than this one. Whatever this beam was, must have had just a little bit higher than this one, because we've got 4.97 times 10 to the negative 19 and 4.75, comparing those. So that's how you use both of those equations. Now on the sunscreen commercials, you'll see things like where it says, blocks out UVA, UVB, UVC rays, blah, blah, blah. And all of those are just different categories of UV rays from the sun. There are 3 types of UV light. UVA is about 320 to 400 nanometers. UVB, here's the range. And UVC, here's the range. Remember that the shorter the wavelength, the more energy that it is. So this 200 wavelength is a tinier, more energetic wave than this one. So our directions are to pick a wavelength within each region, calculate the energy, calculate the energy of the energy associated. That's funny. Calculate the energy of the associated photon. Great. So to make this simple, my UVA goes from 320 to 400. Let's just pick an easy number in the middle. Let's say that our sample UVA is going to be 350 nanometers. For UVB, let's pick 300, because that's between 280 and 320. And UVC, we'll do 250 nanometers for consistency. So quick convert. 350 nanometers. There's 10 to the 9th nanometers for every meter. That's how many meters this is. There's always that pattern, right? If it's a 3-digit number in nanometers, it ends up being blank point blank blank to the negative 7th power. So doing my magic conversion here, if 350 is the same as 3.5 times 10 to the negative 7, I'm not going to get my calculator out to do these ones. I'm just going to go follow the pattern. 3-digit number will just be to the negative 7th. So these are all of our wavelengths that we're using. This is the wavelength for the first one, And the formula that we're using is from the notes, copy, paste. Energy equals Hc over wavelength in meters. So in my calculator, to get the energy of this wave, I'm going to take H C divided by the wavelength in meters. And what this is saying, I'm going to use my orange marker for energy. The energy of a UVA wave, the one that I chose, is like 5.68 times 10 to the negative 19 joules. This is how much energy is in my UVA. So your turn. This is how much energy was in the UVA. I plugged that 3.5 into here. What's the energy when you plug in the 300 nanometer or the 2.5 nanometer? So pause this video if you need a little bit more time, but the calculation is going to be the exact same as before, but instead of having, 350, I've got 3.0. Your answer should be 6.62 times 10 to the negative 19 joules here. And on this one, instead of being 300 or 3.00, we're going to switch it to 2.5. The energy of this one is 7.95 times 10 to the negative 19 joules. And this is what we predicted, right? We knew that this one, 250, was a shorter wave. It only takes 250 little spaces to get a full wave in. The next one took 300 spaces to get the wave in. This one took even probably longer, 350. The squishier it is, the more energy is. 7.95, 6.6, 5.6, they all have the same ending, so we can compare them. UVC has more energy. It would be the most damaging of the UV waves. So on number 12, we're just going to graph the data. When our wavelength was 250 nanometers here, when the wavelength was 250 nanometers, the energy was 7.5 times 10 to the negative 19. So we're going to graph at 250. We're going to have one at 300 and 350. Those are the ones we picked. These are our values. And since all of them are times 10 to the 19th power, on the y-axis here, I'm just going to write times 10 to the negative 19th power, because then when I do my scale, I don't really have to worry about it. I can just go from, 5 to 8. So we'll do that little zigzag thing. 5, 6, 7, 8. And then, of course, times 10 to the negative 19, since they all have that on there. So at 250, we were at 7.95, which is like here. At 300 nanometers, we were at 6.62, and 350 was 5.6. Looking at my line of best fit, it kind of looks like it's going to do that, where the energy is going down, and here's our wavelength. In nanometers, and the energy is in joules. Anytime that you've got a graph, if your graph is doing this and goes up, that's a direct relationship. An inverse relationship is when you've got this going on. That kind of looks like what's going on here. Whoop. I would say wavelength and energy are inversely related. What relationship exists between frequency and energy? We know this one from the notes. When we have low frequency, we have low energy. High frequency, high energy. So when it's running 2 ups or 2 downs, they're kind of running same. That's a direct relationship. And I'll let you figure out from, this is in note 17, what's the relationship between the wavelength and the frequency? You should have enough information to complete this, because if you have a high frequency wave, you have high energy. Low frequency, low energy. So make sure that you go back and do all the ones that we skipped, just those 2 or 3 problems. And this again was homework 3.2.